Yo, what's up, guys? So this time, we're gonna talk about another like graph problem, which will be involving to another very classic algorithms, right? So let's take a look at this problem number 743, network delay time. So you're given like a network of nodes labeled from 1 to n, and given times, right? Basically, each node has a time, right? It's a it's a it's a directed graph basically. So from 2 to 1, the time is 1. From 2 to 3, time is 1. And from 3 to 4, time is 1. And you need to calculate how many times, like how long will it take for all the signals, for this signal to be propagated to all the nodes, right? So for example here, like this one can be a signal to 1 and 3 at the first time, right? At at the same time, and then from 3 to 4, that will be 2, right? From here, that's 1. This is also 1, and from here, that's 2. Basically, because since 1 and 1 moving from 1 1, they can be moved at the same time, right? Another example, let's say there's a 1, 2, 3, 4, and let's say there's a 5 here, right? So let's say this is a 1, 1, 1. Let's say there's a 2 here, right? Then what's going to be the total number here? See? So on this side is 2, this side is 3, right? So the total number will be 3 in this case. Hmm. So now with this in mind, we can convert this problem to it's like a very classic problem. So we need to calculate what is the longest length from the starting point to any of the node, right? Any of the node, because that longest length or longest value or longest path will be our final result, right? Because that's the one that's will take the most time, right? So, and for all the others, the signal can be traversing to all the nodes at the same time. Only the ones with the longest path will be our bottleneck here. So which will be the time it takes for the signal to travel to all the nodes, right? So since we now it comes down, the uh we need to calculate the shortest path. Basically, for this one, for to get to 5, we need to get the let's say there are like many paths to get to 5. Let's say there's another like 5 here, right? We need to get the shortest path, right? That's because the shortest path will be the time which we can which will which will take. Let's say if this path takes 1 plus 2 equals to 3, and let's say this path takes 3 and 7, 4 and 7, but still the time from 2 travel to 5 will be will be bound to the shortest value of the path, right? Then this problem comes down to for each node, we need to calculate the shortest path from the starting node, and in the end, we just get the biggest the path the biggest distance for all the nodes, and that will be the result, right? Cool. So and then today to calculate the shortest path for nodes, we're gonna use this algorithm called Dijkstra algorithm, right? So what does the Dijkstra algorithm do? Basically, the Dijkstra algorithm will be using a priority queue, and it's an advanced a variation of the breadth first search. So the basic structure is still the breadth first search, but it's a little bit different because the queue we're using here will in the regular breadth first search, it's going to be just the regular list, right? But in this case, we're gonna use the priority queue. The priority queue. So we're gonna input the every time when we add a list, when we add a node to the priority queue, we'll be adding like a tuple, which the the first element will be the distance, the current distance from two, right? From the previous node plus this node, right? And then the second one will be the node itself. And with that priority queue, and every time when we pop a node from the priority queue, we can always be sure we are like processing the smallest distance at the moment, right? So that can lead us all the way to the shortest path of that node. Okay, so let's try to implement this. So with that, first we have to like always we need to construct a graph first, right? Gonna be a list, right? So and for times, right? For times for time, this is gonna be the edge actually. So uh, since okay, so it says UVW. Okay, we'll just use UVW. UVW, right? In times, right? We're gonna since this is a directed graph, we're gonna have like U, right? Append, right? So what's gonna be the value of this dictionary here? So the each value will be a tuple, like the W is the time, I think. Yeah, so it's gonna be the W and V here. It's fine. Yeah, let's do a WV or VW. It doesn't re VW doesn't really matter here. So tuple is the node and the value to get this node, right? The time to get this node. And then let's do a Dijkstra, right? A Dijkstra algorithm here. Like I said, we need to import a priority queue. You can use a heap queue, but I prefer use the priority queue. So you see, I think it doesn't really matter which one you use. And okay, so with the Dijkstra is we need to have like distance a dictionary to store the all the all the nodes distance in this one. So and remember we since we're getting the smallest or the shortest path, shortest distance to this node, we're gonna initialize each of each node to be the maximum value so that when we compare it, we can always get a smaller value, right? And so it's going to be I, right? System dot max size, right? And in for I in range 1 plus 1 to n plus 1 because it's 1 to n, right? So and then after that, we also need to set for the starting point, for the starting k here, right? Remember, the starting node will always have distance 0, right? That's something we need to keep in mind. And you know what? I'm actually so for this for the in although it won't be useful in this problem, but I'm going to also include that parent arrays here just to make this Dijkstra algorithm complete. Because what happens is sometimes besides like getting the shortest path, you're also to print out the path the path the actual path to lead to the to that node, right? So you are supposed you need to print out from 2, 3, and 4. So for that case, we also need to store like a parent's node, a parent's dictionary to store each node's parent, so that later on, if you're asked to print out the path, the actual path, you can loop through the parent to find trace it back to the starting point. And with that in mind, right? So if and as you guys pretty already aware of that, then we have to add this starting point with none, right? Because that's when we stop this while loop traverse back. Every time when we see the parent, the node of the parent is none, then we know we find the root, and then that's when we stop. Okay, and then we're gonna have like priority queue here, right? That's the actual queue here we're gonna use to do our breadth first search and collections, right? Prior no, no, we don't need to do collections. We already imported that priority queue, right? And so priority queue we put, right? And when we put into this priority queue, we always start uh, from this k here, from starting node. So it's going to be the 0 and the k, right? With the rank or with the distance at the beginning, so that the priority queue can sort based on the first value here. And then while, right? While priority queue dot queue size, right? Queue size is greater than 0, right? And then we do the following here. Uh, yeah, we also need to have like another like set to 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 record which node has been processed. Why? Because since like this is a graph, right? Which means same node can be added into this priority queue multiple times, right? Because let's say there's a like node 1, 2, 3, 4, okay, here, and 5. I'm just drawing it randomly. And so what does that mean, right? It means that this 4, right? It could be added to this queue multiple times. Let's say there's like a 1, 2 here, 3, and 6, and 1, right? So we're doing the breadth first search, right? Um, well, actually, this is like another good example, but I will just okay, let's 12. Let's make it 12 here. So when we do the breadth first search, we add all the neighbors to this 2 and 4, right? For 1, and then we have 2 and 4 in the queue. And then we process this 2, right? And then we could, when we process 2 here, we will also add 3 and 4 here, right? Basically, when we process 2, we'll add 3 here, and when we process 3, we also see a 4 here. And then when we see a 4 here, we'll also be seeing, okay, oh, there's another like 4 here, so with a different length, which is like 3 plus 6 plus 1, which is going to be 10 here, right? So at this moment, we're going to have like two array, I'm sorry, 2 element for 4 in this priority queue. And later on, right? So in the later on we'll be popping those 2 elements of 4, right? So but since we have this priority queue, and the first one will be popping is the 10 4, right? But there's like another one. So let's say for example, this is the queue, right? This is head and this is tail. So at this moment, when we process pop this 10 here, remember there's like a 12 and 4 here, right? Somewhere on this side. And we also we because that's the one we want to process, right? And we don't want to when the next time when we see another node, another element, when we pop this one, we see, oh, it's 4. It's already, oh, we have processed this 4 before, because since we're using like a priority queue, the first one is always the one we need, right? Because when we see a 12 here, we don't want to see, oh, let's update the distance for 4 to 12, because we know the first one got popped is the correct result we need, right? So okay, with that in mind, let's do a check here. Okay, so that's why we need a scene here to record which node we have been processed, which means which node has been popped from the priority queue. And okay, so now we have what's the distance? We pop the priority queue, right? Every time do a pop the first distance and node, right? Equals to priority queue dot get, right? So this will give us the shortest distance we currently have in the queue. The queue is the queue stores all the nodes it's ready to be processed next, and we get the smallest one. That's why we keep looking for the smallest path next. And since we are popping that node, then we know that node has been processed, right? And then we just add that to the same set. Hmm. And then for all the neighbors, right? For all the neighbors of that node, right? Yeah. For neighbor in the graph, since we already have the graph on up above there, we just use that to try to process all its neighbors, right? And node, right? And then for each of the neighbors, what do? First we check if this neighbor has been processed, has been seen before, right? If it's already been seen before, then we just simply ignore it. If not in scene, right? Then we check, right? Then we do what? We do a we do a comparison, right? So we're only adding this neighbor to the queue if this neighbor has a smaller distance with the previously recorded distance for this node, right? Otherwise, if it has a longer one, there's no need for us to process that node, because for each node we are always trying to get the smaller result, right? Basically, what do we do here? So for each neighbor, remember in the neighbor, each neighbor is also like, so okay, sorry. So each neighbor we're also storing two values here. So the neighbor and the next, we can call it the next distance, right? Because that's the next distance from this node to the neighbor, right? And then if it's not seen, we're gonna have a new distance, right? Let's call the new distance here equals to current distance, right? Plus the next distance. That will give us the new distance from to through through the current the node and to the neighbor, right? And then another if check here, right? So if the new distance, right? If the new distance is smaller than what we already have for these neighbors, smaller than the distance distance neighbor, right? And then we add it. So that's why we initialize this distance with max size. So in this case, the first one can always be added because that's the max number at the beginning. And then we do what? We do we sh yeah, we add it to the priority queue first, right? We do a put And when we do the put, we see there's a, like the new distance, right? So the new distance and the neighbor basically, right? So because we know we find a smaller one, and then this one can be a candidate, which will be processed next, and we will leave everything else to the priority queue to tell us if it's really the candidate or not, right? And then let's yeah, so since we already find one, we also need to update this like the neighbor, this the distance of this neighbor with the current new distance, right? That's how we track of the smallest distance for this node. And here, right? So I'll be also updating these parents here. But although we're not using these parents, but I'll complete the whole algorithm here. So every time we see a smaller one, we know, okay, so this is a better path, right? And this can be a better path. So we just keep updating. So basically for the parents, right? The parents basically now the parents of the current neighbor will become that node, right? We just keep updating this one until we find a perfect path. And so let's see. Until that is done, we already have that. Okay. I think, yeah, once that is done, we have everything in the distance here, right? And then we just need to get the answer here, right? Once this while loop is done, we have all the shortest path stored in this distance dictionary. So we just get the max from them, right? Because like I said, we need to get the maximum uh, distance from for all the nodes. That will be our time in this case. So it's going to be distance dot values, right? So can we return the answers here? Probably not, because it also asks you to check if it's possible to traverse to all the tree, right? Basically, if there's like one, let's say in this case, there's like 5 and 6 here on this side, right? And we're starting from 2 here. Since basically if there are like 2 components in this graph, in this case, there's no way you can propagate the signal to these nodes. So how do we check that? Remember, so we're only traversing from this sub node, from this sub graph here. This is untouched, right? What does it mean? It means that for the untouched ones, the distance for those arrays will be what? Will be max size, right? So we just check here. We only return as the answer if the answer is smaller than the max size, the system max size, right? Because if there are some max size in the array, so this one will be max size, which means there's like a disconnection between some of the nodes. So else, right, -1. Yeah, I think that should do it. Max size. Max size. Size. Yeah. Cool. So it works. All right. Basically, a classic Dijkstra algorithm here. We use like a priority queue plus a distance and array and a scene array and a scene ones to prevent reprocessing the same node with a longer distance, right? So that's what we check here. What we do, we check here. If the neighbor has been seen before, which means has already been popped from the priority queue, then we know there's no need to process it again because we know the first one got popped will have a smaller distance, and the ones of after doesn't need to be processed anymore. And so let's take a look at what's in at this moment, what's in the parents, right? Let's do a debug here. Uh, Okay, so at this moment, see, so this one, the parents, so any node from the parents will have the path. So basically, if you want to find a shortest path itself, if you want to print the path for for any node, right? So what do you do? Uh, Basically, you just do a simple while loop here, right? You can just do a simple while loop here, and you have like a path, right? Path going to be like a list or something, right? And then let's say we want to like starting from the from from two. Let's say that we want to start from two. We just do a while, right? While while parents, I think while parents, yeah, we do a current node, current equals to two. Let's say, for example, while parents, I think it's parent, right? While parents current, right? Uh, it's not none basically, right? While if it's not none, we just do what we just uh path dot append, right? Append what? Append parents current, right? That's our basically we're traversing back, right? And then we just do a current, right? Current equals to what? Equals to current dot uh equals to parents dot current, right? That's what we are keep traversing back to the until this max until this parent current is the it's none. So when it is none, we know it's the first one. And well, actually, we should do this. Yeah, that will give us that can print the last element for us. Yes, yeah, it should be while current. Yeah, while current, and we just keep assigning this current until this is empty, and then that's what when we print out everything, right? So in the end, we're gonna have a path starting from the last node to the beginning, and we just return the path, uh, and we just reverse the path, right? That will give us the path from the root to the to this current node. Okay, cool guys. I think that's it for this problem. Yeah, thank you so much for watching the video, and well, I'll be seeing you guys soon. Thank you. Bye.